Right, so the purpose of this video is to talk about phase angle, phase difference, and superposition of waves. So phase angle. Now on the left side here, I have a unit circle that goes from 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then back to 360 degrees. So it's very clear from math that the distance around the circle, the circumference, and the circumference around the circle covers a total angle of 360 degrees, which is equivalent to 2 pi. Now, this is very similar to the motion of a wave, or we can compare both of them together. Now, as you can observe from this wave-like motion, as the arrow is moving from 0 to 90 degrees, you would notice that at 90 degrees, you have the crest of the wave, which you can see here on the right side. And as the arrow moves down to 180, you're back to the equilibrium displacement. And as the wave moves to 270, you have a trough, and it goes back to 360 degrees, you're back to the node, or you're back to the equilibrium displacement. So we can always compare the unit circle or circular motion to the simple harmonic motion you have in a wave. This is a very important comparison because it allows us to be able to work on understanding what phase difference is. And it's very important in the superposition of waves. And also we're going to see applications of this in diffraction in later topics. So let's talk about phase difference for a moment. Now we have two waves, the blue and the green wave. The question is, I have two questions. The first one is, what is the phase difference? And the second question is, which of these waves is leading the other one? Or which one is lagging behind the other? The key to understanding this question is understanding the previous slide that I just explained. And if you look at the blue wave, for example, at a given time, right? If you freeze time, at a given time, you would observe that at this time, t, which we don't know, just for the sake of it, let's say t equals 1. What we have here is that this wave is already at 90 degrees. And while this wave is at 90 degrees, you can see that the green wave is still rising. It hasn't gotten to 90 degrees. In fact, the green wave takes a later time, or takes more time to attain 90 degrees. So what you can observe here is that there's a time delay, right? There's a time difference or a time delay. So basically, you have the blue wave attaining 90 degrees, and then the green wave attains that later on. So it's quite obvious from this already that you have the blue wave leading the green wave, or you have the green wave lagging behind the blue wave. Another way to see this is throughout the rest of the graph, you have the blue wave arrives at 180 degrees first, and then at a later time, the green wave arrives. Or the blue wave rises, right? Rises again to 90 degrees before the green wave rises. So the blue wave is always leading behind, or leading ahead of the blue wave. Now, the difference in that lead time, or in that lead distance, depending on what this axis represents, is going to be the phase difference. I'm going to show you in a later video or in later slides how you can calculate this phase difference. But just understand that this delay, or this leading or lagging, is usually what we use to calculate the phase difference. And a very key way to understand, or to explaining this before you see it, is to know what this difference is, whether this is a time axis or it's a displacement axis. If you know the difference, you divide that by the total time period. If this was a time graph on the axis, on the x-axis, or if this was a displacement on the x-axis, if you know this difference in length divided by the total wavelength, multiply that by 2 pi, you'll be able to find the phase difference. I'm gonna show you an example on this later on. All right, so phase difference or phase shift. Now let's look at these four graphs. The first thing is we have wave A and wave B. So if you look at this picture very clearly, you have wave A arrives at 90 degrees, while wave B is still at 0 degrees. So 90 degrees minus 0 degrees is basically, you have a phase shift or phase difference of 90 degrees. So A is ahead of B. A leads B, or B lags behind A. Another example is here, you have B right? It's actually the same thing, but it's just reversed. You have B, B starts first and then gets to 90, while A is still at 0. And so you have the same thing. You have B is ahead of A. And that's a very clear example. Well, these are very two clear examples. Now, in this third diagram, what you have here is they both start at the same time. However, or they seem to start at the same time. However, from what you observe, A is going up to 90 degrees, while B is going down to 270. And of course, from what you observe in this diagram, the phase difference is actually 180 degrees. And you can tell why, right? You can see that this is 90, and while this is 90, this is 270. So 270 minus 90 is 180 degrees. Now, of course, when we look at superposition of waves, you'll see that this is going to lead to a destructive interference. And so that's the key here. Phase difference of 180 degrees always lead to a destructive interference. We'll talk about this later on. Now, what about the last diagram? In this last diagram, both wave A and wave B are superposing each other, and there is no difference, or there is no one leading or no one lagging. So they're perfectly in step with each other, right? They're perfectly in step. When they're perfectly in step, you have 0 degrees phase shift or phase difference. All right. So now here's an example of applications of superposition of waves where you have a constructive interference or destructive interference. Now, what is a constructive interference? Constructive interference happens when two crests or crests of waves interfere or superpose, and that causes doubling of the amplitude. All right, and destructive interference is the opposite. So, like I explained to you in the previous slide here, when you have the crest aligned with the trough, you're going to have a cancellation, or when you have a 180 degrees phase shift or phase difference, you're going to have a cancellation of the wave. And that's what you can observe if you look at these two waves. So let's look at this. Right, when this is aligned, when you have crest to crest, you're going to have this to be maximum. Right, and when you have crest to trough, you would have a very straight line. So you can also look at this using this particle, the red particle over here. Right, this is a simple harmonic motion because the wave is moving in this direction, but the particle is oscillating up and down. All right, so when you have a crest with a trough, you would have 0, and then that motion continues. Okay, let's look at, so this diagram basically explains what I just explained in the previous slide. You have two crests aligned with each other, you're going to have a doubling of the amplitude of one of the waves. Or when you have a crest aligned with a trough, or when you have a phase difference of 180 degrees, you're going to have a straight line. This is called destructive interference. Constructive interference usually would need 2n pi of a phase difference in order for you to have that. So I don't need you to memorize this for now or try to understand this now, but if you already do, good job. However, we're going to talk more on this in class later on. Now, for you to find out more about superposition of waves, I would highly suggest and recommend that in 4.3, you go back to 4.3 and watch the following videos here and revisit the material. You can also use a simulation to help you understand this a bit more. Principles of superposition of waves. This is a very important concept because it allows us to know what would be the resultant wave, or allows us to be able to plot or determine the resultant wave when you have a superposition of two different waves. So in this example, what we have is the blue wave with the green wave, and the principle says or states that at a given time or the given distance, you just basically add the two distances or the two displacements. So what do I mean? Right. So for the green wave, or the red wave rather, the red wave has at t equals 13, oh sorry, this is probably 1.5, my bad. At t equals 1.5, you have the displacement of 4. And here you have the displacement minus 4. When you add those two displacements, you get a resultant displacement of 0. So this superposed wave is going to have a displacement of 0. Same thing applies here at t equals 1.5. This is 4 and this is minus 2. And you add up to get a resultant displacement of 2. I'm going to